the absolute value of x is really the same as x and negative x for x greater than or equal to 0 and x less than 0. So in order to use the definition of the derivative to show that that derivative at 0 does not exist would mean that we have to take the definition of the derivative almost twice. Because we're not going to have a way to be able to simplify it by putting absolute value of x plus h minus absolute value of x all over h. That's not going to help us. What will help us is seeing it as two different piecewise. So you would take the limit as h approaches 0, and we'll start with the top one. So you can group the x's, they cancel, you get h over h, which turns to 1. And we get 1. For the second part, you take the limit as h approaches 0. Now it's negative x, so it's negative x plus h minus a minus x all over h. So again, it's negative x plus h minus a negative x. So I get so now x is still cancel, h is still cancel, but this time we get negative. So 1 doesn't equal negative 1. So because the left-hand limit and the right-hand limit do not equal each other, the derivative does not exist. And that gets into kind of like where we're going with how do you find differentiability? Differentiability comes from continuity. Since they're not continuous at that 0, then we're not going to be differentiable. Because the left-hand limit doesn't equal the right-hand limit, therefore the limit and derivative do not exist. Does that make sense?
Yeah, I just didn't know. I didn't know it had to be like continuous and if you can derive those like the same thing.
Yeah.
So I didn't know you had to
Like make it a piecewise.
Yeah.
So did you try to do it as like an absolute value? You're like, eh.
Yeah, but I didn't know where to go from it. I didn't know you had to prove that it wasn't continuous. But that makes sense.
All absolute values have to be turned to piecewise functions in calculus. Pretty much no matter what. Anytime we have an absolute value, treat it like a piecewise, where you have the positive and the negative side.
So I don't know if it's like different because it's like derivatives, but like if you graph it, like 0 exists, so I don't get like.
But no, it's asking for f prime of 0.
It wants the derivative of it.
It did
I
say
don't
like.
understand what you mean by derivative.
So the derivative is the slope of the originals. So an absolute value function at 0 has a point,
Yeah.
right? Here's our original function. The left derivative in this case, the negative stuff, all values less than 0, I get the number negative 1 when I find its derivative for this part of the piecewise. The slope of the absolute value on the left side is negative 1. Right? You would agree the slope of this is negative 1.
Yeah. So is it derivative?
The derivative is the slope of the original.
So is it just the slope of a piece of it?
The piece is splitting in 0. Yes.
Okay. So like that's all a derivative is.
Yes.
Okay.
Yes. Derivative is slope. It's literally the definition of a derivative is the rate of change. It's just that, like, we're going to look at functions that are cubic, And we don't really say that the rate of change of a cubic has a slope. Like, we don't describe cubics as having slope because we're not linear. So this is easy to see right now because it's linear. So you say 0 exists.
Yeah.
I agree. 0 exists on the original. However, the limit from the left is -1. The limit from the right is +1. Does the limit exist at 0? The left-hand limit equals -1 and the right-hand limit equals +1. Does the left-hand limit equal the right-hand limit?
This is just for the derivative.
Just in general, it's still the limit. Yes, yes. Of the derivative. Yes. We're down. The original we believe, and no is continuous.
Yeah. Okay.
That I'm not arguing. We are now talking about continuity
Okay.
of the derivative. So when I'm talking continuity right now, I'm looking at this. I'm not talking about this.
So it's basically just asking if our slope has some constant number, basically. Because, like, if the line changes, then the derivatives are not equal most of the time.
Yes. But, like, slope can change slowly over time.
Yeah.
So, like, a quadratic is continuous
Because
and differentiable at all points.
yeah, because it has that parabolic shape, and that slope is technically not the same, but it follows the same pattern because it's a square.
And it doesn't have what we're going to talk about tomorrow, which is what we call corner. So this has a sharp, distinct change in direction. Any sharp, distinct change in direction will have two limits of the derivatives not equal each other. Because the slope to the left, really, really close to it, it's -1. The slope to the right, really, really close to it, is +1. They will never equal each other, and you cannot account for all of the points in between. So you talked about velocity being 0 at a maximum. This cannot have a derivative of 0 because it doesn't have like a smooth maximum. It has a pointy maximum.
So when you have the limit h approaches 0,
Yes.
that, like, what it's equal to is no longer a y, it's now the slope.
Correct.
Oh.
Because this is the limit not of the original, but using the definition of the derivative.
Okay.
This is the derivative of that. Does that make more sense?
I think so.
Like, I think that's where we're confusing, like, original limits with, like, the definition of the derivative.
Yeah. Yeah, I think that helps. Thank you.
You're welcome. So if you go, okay, let's talk about the homework then, right? Number 1 and 2, without, like, I literally took this out of the bin, right? Like, I have no work in front of me. The answer to 1 is -2. The answer to 2 is -4. Because the definition of the derivative says the derivative of a line is the slope of the line. The derivative of a line will be the slope of a line. So derivatives will always be the function prior. So do you remember back in the day, and it was probably maybe like algebra, and you talked about the degree. So like degree of 0 is what type of function? Something has a degree of 0, what type of function is it? All right, let's go easy. Degree of 1 is linear.
Oh.
Degree 2 is 3. Nope. They just go to whatever, 6, 7, 8 degree. So what's 0?
Straight line.
formula. Not wrong, it is a line. A linear function's derivative becomes a constant, becomes the slope of that original. Look down at examples 3 and 4. Your answers were linear functions. The answer to 4 was 8x, right? Or, I mean, the answer to 3, sorry. Animate face. And I was like, wait, nope, just said the wrong answer. The answer to 4 was negative 6x. Because a quadratic becomes linear. Because the slope of a quadratic is a line. Because it's not going to just be a number. Because the slope is constantly changing along it. So it's linear, so you can find all those constant changes in slope. Number 5, you got negative 8x minus 5. Number 6, you got 6x plus 3. 7, you got negative 3 halves all over the square root of x. Or, well, negative 3 over 2 square roots of x. Maybe.
Okay.
Actually, no, you probably have the original and then everything I just said.
I got negative 3 over 2 square roots of negative 3.
Yeah, over the original. So I said
Oh, yeah.
like at first I said over negative over the original. Yes, we can do that one.
Oh, that makes sense now. Because if you do.
Okay, so far?
I used the x and a one.
Yeah, so we're at h is u of a. Or you did f of x minus f of a.
Yeah. I thought they were easier. Canceled out easier.
I multiplied by the conjugate, so the definition of the difference of squares says the middle terms cancel, and then the same square root times the same square root become values.
Should I change them all to x's?
Do you have a's?
Yeah.
Where the heck? Oh, okay, you put from that. And you just multiplied it by itself. This is a subconjugate.
Like this became 0, so it went away. So I plugged that in. I just didn't show the line where I plugged in 0.
Oh, then you literally added them together.
Yeah, because they were, you can add together radicals that are the same. So like you could add 2 square roots of 6 plus 3 square roots of 6 to get 5 square roots of 6. But you can't add like 2 square roots of 7 plus 3 square roots of 6. Because the 7 and the 6 are the same.
Is the 8 2 over the original?
8? 4. It should be 4 over the original.
I got 4 over 2 square roots of the original.
So you simplified. So you got 4 over 2 square. Yeah. So you have 2 over the square root of 4x minus 5. Yes.
Now I see how the power rule works.
It's actually called a chain rule.
Figure out the first.
A chain rule
You
is a
multiply
power
the
rule.
first term and then bring the bottom one to the bottom. Right? Similar.
There's some other stuff in there. That's why it even took me like a minute to like think about it.
Yeah.
Now 9 and 10, those ones, the rules are much more complicated. So did you get 1 over x plus 2 squared for number 9?
I got -1.
-1 all over x plus 2 squared.
And then 10 is
So negatives cancel there.
10 is
And you're
4
gonna have
over
4.
over the thing.
Does it matter if you like factor it out?
Yeah.
I always leave it like even like the ones before like I'll have like the thing plus the thing on the bottom, and like this one I have the thing times the thing. I just don't know what's saying it. It's like, do I have to like simplify it? Like I have that instead.
No,
of
that's fine.
Okay.
You're good. When you were saying that, I was like, what's the thing times the I was like,
I just didn't feel like saying like 4x plus 5 or whatever.
that's why I just walked over, looked at your paper, I was like, I don't know what
The
you're
thing.
talking about. What's the thing?
Seems like the signs change and then the tops are squared and the bottoms are squared. Or this one.
They're easy because the sign is in the
Top can't be squared.
Yeah, the top
Technically, if
isn't squared.
Yeah, 'cause
That's
the
not part of
the
the
next one's 2.
It's hooty high minus hidey ho all over homo. So that's where you're getting the bottom squared.
What?
Yeah, but technically.
Don't worry, that little saying I just said you
Technically,
will like
I
memorize
thought
so
we had
soon.
4 over. Wasn't it 4? For 10,
Yeah.
wasn't 4 over that? So
Yeah.
2 squared is 4.
That's all why it's for.
Oh, I got 2.
That's all why it's for. Okay. Anything else on 9? So it sounds like we did pretty well with definition of the derivative. Sounds like you guys can write out limits and do your algebra.
Are we going to be able to see our test?
Yes, we're gonna go over this today. Let's do one more crazy one.
This one was on our homework.
No, it's not. Your homework's x plus 2, right?
No, it's different on the board than it is on the paper.
Oh, never mind. I was looking at it.
This square.
The squared's not on your paper?
Yeah.
Put the squared on your paper. Because that's what makes this problem the problem.
Because our example is 1 over x plus 2.
Right, that's why this is totally different.
So just completely change the equation then.
On your paper, just add a square.
Just make it.
Okay,
Just
cross
change
out
the
the
people.
cross out the problem and write down that problem.
different.
I know.
Yeah,
I
me
know.
too.
Over
This
X
is
plus
what
I
happens.
know,
I know.
I
I understand
understand.
that. Just cross it out and write down.
Is it?
We get that it's different.
Oh, I think I changed it because of your homework. Like, I
Oh.
think, like, you know what I mean? Oh, no. It should be this. So, this is asking for an x equals a. So, what that means is you either, if you do the limit as h approaches 0, where you normally have an x, you need to put an a. If you want to do the other one where x approaches a, you can too. But I'm just going to do it as a plus h for all of mine. So it's 1
I'll do
over.
the other way and see if we get the same.
Don't do it on the board so they can see it. Or like on that board. Ugh. Well, we better get the right same answer. It's too many fractions. Well, we're going to get rid of them. How do you get rid of fractions? Common denominators. So, don't try to FOIL it first. Move it all there. Don't try to FOIL it first. Move it over there.
Will the following students please report to the office? Veronica Hess, Madison Smith, Alyssa Wright, and Ashley Navarro.
Is that better, Michael? Way less fractions.
It's
Common
better to look-
denominator, and then a fraction over a fraction. It says this is really like 1 over h, so you multiply it to top and bottom. So that's where my h came from.
That's just the top.
Top is the common denominator still. Bottom. Everybody else okay?
It's gonna take a second.
Boil it out now.
So you just take the denominators of the numerator and then kind of smush them together and then multiply the denominator by that. So is that because it's the same numerator in the numerator?
Yes. They're ones. An answer.
Huh?
What?
They take the same amount of steps.
Did they? That's what I was just going back to look at.
I mean, yours took, well, no, yours still took the same amount of days.
And technically, yeah, he showed us plugging in, like, here's my plug-in 0, here's this plug-in A. Like, there's our cancel. In my heart of hearts, I'd probably, and he probably could too, ignore writing this step. Like, I could have gone from here to there. I think, like, there's a step in there, don't could, like, skip too. So again, very similar. This one, you have to FOIL, where that one you factor. It's like kind of opposite, like they're friends, you know? FOIL and factor. I like to FOIL more than I like to factor. God likes to factor more than I like to FOIL. And now you got to see both. But not Spencer. We'll send it to him.
I just think that's much easier.
That's what I said, like, again, like, it's what you're good at. Like, I have just done it this way for so long. It's my comfort zone.
Where do you put the 1 when you FOIL that out?
Which one?
And then the, not specific, my bad. And the numerator of both in this case. No, not both in this case, what I'm saying.
I'll point to it on board.
So when you have this,
Mm-hmm.
how does it get to that?
Foiled it.
But do you start here, and where's your like inner outer thing?
Yeah. A, a squared. So that's f first. Like, there's my last. Outer, inner is always going to be the same, so I just double.
Maybe it's wrong to this. But the triangle thing, but like.
Yeah, that's the Pascals.
Oh, I got you.
Always the same, so I double.
Then you have plus 1. 1 plus whatever. So you think
Negative,
negative?
because it's a negative outside the parentheses. So negative went all the way through. Better?
Yep.
That's why I said come point, because you were asking me, I was like, I don't know. Pointing. Oh.
So do you, oh,
Go ahead.
sorry, my bad.
I'm just going with those two
Is
copies.
that the same process for the denominator as well?
You don't FOIL or factor anything to the denominator, you just rewrite it. Always. Never factor or FOIL. Just rewrite the denominator. Like literally all of this gets rewrite.
Oh, I thought you meant like in a different way.
Nope, just rewrite. Alright guys, we are learning notation today. So, this notation is the notation we are going to use for the rest of the year. We have essentially 4 ways that we can write the word derivative. Y prime and f prime of x. So you say the word prime. Prime means 1, right? Y prime means first derivative. Prime is 1. That is, so like the far right side is like why we use them or how we use them.
Does this say
I'm rewriting it.
No, the other thing. Does it say WRT?
Yes, with respect to. WRT stands for with respect to. WRT, with respect. What are you giggling about?
I thought it was a wart.
That was like another quiz.
Derivative of y word x.
Yeah, I thought it was like another way to write it, like wart x.
Every time I say WRT, now I'm going to think of that.
Wait. What's the D other than derivative means?
What?
So like, does the D just mean derivative?
Yes.
So when you're saying y with respect to x, you're meaning that your y is dependent on what your x is.
Word x.
Yeah.
So how does the f change?
Hold on. Differentiation. Yes, I spelled it right. But if you can't repeat your question, how can I answer?
That's a good point. So when you're saying it has respect to
So you're taking the derivative of y
okay.
with respect to variable x.
So
If this said dy dz, that would be the derivative of y with respect to variable z.
so what is plus here? Plus what the
Almost proof you're on video. What?
the df the f itself. So the function thing.
Yeah.
But like
Is it emphasis on or emphasizes on?
Does it matter?
Because I can't tell. if
Well,
that's one
okay,
word
so
or-
emphasis on is fine, or it would be emphasizes function name. Like it's what or the other. Like not emphasizes on.
I
It would
didn't
be
know how to-
emphasizes
I didn't
or
know.
emphasis on.
I didn't know
Do you
how to
even
spell like
English?
emphasize. I didn't know if it was like em, and then is like the is is like combined. Is like.
no, it's
Are you really picking on my handwriting today?
I'm just, and then the second one, I don't know, is that like a W or something? Names both variables. That's a D?
Yeah, names both variable,
I
uses
was like,
D for derivative.
Alright, Dom, how do you write your W's?
I think I erased a little bit of that letter when I did this because I forgot to
that
change
makes
it back from like my eraser to my pen. So then I was like, oh, but I didn't realize that's his name. So Leibniz is a name. Leibniz is a name, yes.
We need to write that?
It might be a bonus somewhere along the lines. Okay.
So who is that?
Leibniz came up with the notation dy dx.
Okay.
Leibniz, he's French. I don't know where why they don't say, we're going to learn something called l'hôpitaux, and it's spelled la hospital. So. I am making Michael's brain hurt today.
Michael, how is your brain
It's
Did I break it yet? I think it's going to break further when I So, we talked a little bit about, at the beginning today, derivatives and their graphs. Oh my gosh, which one can you read now?
Is that
Differentiation. Because I had to make sure I spelled it right, because I was like, differentiation.
So, what is the difference between?
spelling's on the strong suit.
Mine either.
Is reading?
What's the difference between the emphasis on the function name and the off?
Emphasis on differentiation of f.
Okay.
That's what they
What's
all
the
do,
difference
like
between
all
those?
the cousins.
This is
I took it easy.
df dx versus d dx
Stuck a
f.
hot dog over his head that they were roasting
These,
it on
like,
his-
these are just the ways we can write derivative now. This is how you say it. This is what it does. They're like mini definitions. Don't worry, we're going to use the top 95% of this class. This is for Calc 3, and this is sometimes on
He said that
the
you won't wear
So, back to where I was going, we are going to start looking at derivatives and graphs, because that flows to differentiability, which is tomorrow's lesson, which gets back to the absolute value question we started class with. We're only going to look at smooth, continuous polynomial functions today. Smooth, continuous polynomial functions are always differentiable because their derivative follows that degree thing that we talked about previously at the beginning of class 2. So it was a great intro to do that degree scenario. I have for you a chart that you are going to call your best friend. Yes. What do you know about my chart?
I flipped to the next page.
I know. I was like,
So when you say it's differentiable, you mean it, you can take a real derivative of it?
yes.
Wow.
So to be differentiable means it has a derivative. When we talked about graphs back in the day, we used to say, okay, where is it increasing? Where is it decreasing? What's its max? What's its min? What are its zeros? Those same points are still concerns. But we're now going to use those points to help us graph derivatives. So, we still care about, is f increasing? We still care about if f is decreasing. We care about if f has an extrema. An extrema is a fancy way of incorporating the words maximum and minimum. An extrema is a fancy way of saying both.
Wait, so if it has both, it's an extrema, or if it just has
Either or. So a quadratic has an extrema. Has one extrema, and that would be at its max or min, depending on which way it opens. We care about if graphs are concave up. Concave ups are your smiles. So if you're concave up, you're positive, you're happy. It's like a smile. Concave down, it's open down, looks like a frown. So you're negative, sad. The last one is called a point of inflection or a point of interest. A PPOI, a possible point of inflection. Now, if the original graph is increasing, so let's just take a graph you kind of know. No quadratics, right? Problem is I can only get half of this done. This graph is increasing, we'll say, from the beginning to A. The derivative of an increasing graph is positive. Because if you think about tangents or derivatives, they're the slopes. Can you see how all these little tangent lines would be positive? So if f is increasing, the derivative is positive. So if f is decreasing, your derivative is? How do I go from a positive to a negative? Or, better yet, what happens at the max of a quadratic in terms of its velocity?
Zero.
Right? You get that? How do you go from a positive to negative? You have to cross
Zero.
because it's not positive or negative. So, an extrema's derivative will be
Zero.
Yay! It all makes sense now, right?
We'll say that. We'll put it in.
Here's what's really nice about my chart. If it is concave, and we can't really look at the quadratic for concave up, so right, that quadratic I drew is concave down.
So convex.
What those were shapes?
Those are mirrors.
You're a mirror.
This is concave down.
Either convex or
So that original, and you guys in physics know the power rule, right? So this is like negative x.
concave. Negative x squared. Concave or convex?
What would the derivative of negative x squared be? What would the derivative of negative x squared be? Don't worry about it. I just want the kids in physics to know if I want to do it, right? So we don't know that just yet. Do you see how if you plugged in a number to the left of A, though, a negative times a negative would be A, and a negative times a positive would be? This is, we already said 0, right? So negative, that's what your slope, that's what negative 2x would look like. Okay. What is that function always doing?
Slowly getting bigger over time.
Go back to original linear functions. Is it increasing or decreasing? Decreasing. Concave down will always have a decreasing derivative. Concave down will be decreasing derivative.
And I'm assuming concave up is increasing derivative.
Yep. And guess what? Point of inflections are extrema. Because these three here repeat for concavity on the derivative. These three move here. So in terms of the second derivative then, if the original is concave up, the derivative is increasing, the second derivative would be
Increasing. Positive.
What the heck is the second derivative?
You take another derivative of the derivative.
Why would you do that?
so if it is concave down, it's decreasing, or it has a point of inflection, the extrema will be 0. So again, what's the power rule tell you? What's the second derivative? What is the derivative of negative 2x?
Negative 2.
Does that follow all of those rules? That's not really right, but we're going to write it in. Yeah, the three of them, we will know.
We're lost. Like, what the heck's going on?
You're lost on how to find the blue stuff, but you're okay with the chart and what I'm writing, right?
Wow. That's
Okay, wait. On the first derivative,
Yes.
extrema, can it be 0 or is it like on the first derivative column? It's 0. So. And the middle column, where you see. Okay, but on point of inflection, where it has extrema 0, or is it just?
So the quadratic's a bad for this one. Which we're going to do one. Let's just look at the example. You're going to have your chart. Look at the example. Instead of me trying to draw up an example, I created a really beautiful one. It will help make all of this make sense.
the other three spots.
Okay. What? They're blank. You cannot have a second derivative value for increasing. Like, they don't exist. There's nothing there.
Alright.
All right. Graphing f prime from f. Here's our original function. What type of function does this kind of look like? Cubic, right? Because it has two extrema, so it is have a degree one higher than the number of extrema. 2 extrema makes it cubic. So, the slope from here to there is 4. They gave me that. The slope at B is 1. The slope at C is 0. That makes sense, right? C is an extrema, so its derivative should be 0 based on our chart. Therefore, it has a slope of 0. F is increasing from A to C. Therefore, from A to C, these should have positive slopes. So let's talk about that. Where is F increasing? Let's just talk about increasing. We'll call it G just to give it a name. Okay, so it's increasing from A to C. So therefore, if it's increasing from A to C and F to G, F prime from A to C and F to G is what? Perfect. Where's it decreasing? Do you notice how I didn't make my intervals bracketed? Because C is not necessarily decreasing.
Technically, it's not either increasing.
Exactly. So it's why it's, yeah, I heard the whistle too. That's why it's bracketed.
You mean parentheses, not brackets?
I mean, yes. Jeez. So F prime is what?
F prime of this would be negative.
So many colors.
Do you like it?
No, I said, it's enjoyable. You seem like you have a smaller panel than you did before you updated it, though.
I did. I don't know. I lost one. I have way more colors. Then I'm trying to change it. Like I have all these saved ones. And I click them, and then it doesn't go back to them. Makes me sad. You didn't notice?
No, I didn't.
I think you were saying, oh, that's a W.
I did think it was a W.
Yes.
What is this slopes on here? Does it like literally just mean the slope? Like
Those slopes represent the derivative.
like the second slope at D, like that's not the actual slope, right?
At point D, it is the slope. -1 is the slope at point D.
Yes.
But like how?
Because it's
Hey, don't, why don't you
decreasing.
stop laughing?
It's just a derivative.
I'm not laughing, I'm joking. At D, the slope of that line is -1.
Like the point.
Just
is
that
negative?
tiny segment, not the point, the slope.
And how do you tell that?
It gave it to you.
Oh, so you're not supposed to be able to find it.
Not yet.
Okay.
Oh boy, not yet.
But at point G, isn't the slope 1?
Don't laugh.
-1.
If you
No,
know the
G.
formula, you can find any point.
At G,
Right?
G would be 1. If it's at that 1, it would be
if
1.
you're assuming it's the same steepness as that, inverted, it's a little higher.
So the slope
Little.
isn't like the real slope, like you know when you do rise over run, like it's not that.
If you have the formula, any slope of any point on the entire graph. Is that
But
how
like I don't understand how you find that. Like
is that
using the
how-
graph.
Using the derivative.
I'm not
You
asking
can't-
about
you
the
can't-
derivative.
You can't use the graph, quote unquote, because you don't know the value of here, and you have to have the equidistance value there.
Okay.
So
you
remember
can't
the
take, like,
fruit
from-
fly? Wait, remember the fruit fly example?
Yeah.
When I found the slopes of all those fruit flies?
Yeah.
That's what we're doing, but instead of us using points on that fruit fly graph and finding those slopes, they gave them to me.
Okay.
These are, in all technicalities, slopes of the secants.
Okay. So like you could find those if you knew every single point on the
Yes.
graph. That's what I'm asking.
If you knew what the function
Like I
is.
didn't feel like they.
We don't know what the function is. We don't know what the function is. We don't know it.
But if we did, we could find it.
Yes.
That makes sense.
Okay, where is the extrema of the original?
There's 2.
C and F.
C and F. would be extrema. The other 2 she asked and we had to answer.
He answered.
I said it 6 times. Oh, all right. That's it.
Okay, the extrema are at C and F. Therefore, F prime at C and F is
0.
Like your house and put me on the blanket. Okay. Metaphorical blanket.
if the derivative is 0. Let's graph those points. So the first, so you have a blank graph below, right? Or to the side. F prime, we're graphing F prime now. F prime is 0 at C and F. So C is at 2, F is at 6. So on your blank graph at 2 and 6, the derivative is 0. We okay so far? So you know how you asked me about all of those numbers, Miss Hannah?
Yeah.
Those are the points on the graph. So at A, the slope is 4. So the x values stay the same. So A is at x equals 0. The y value will be its slope, which is 4. B is a little bit between like 1 and 2, right? Its slope is 1. That's B. D appears to be at 3. Its slope is -1. E appears to be at 5. It also has a slope of -1. Does the slope between D and E look the same or steeper? Does the line between D and E look the same or steeper?
Steeper than one.
So like if this is at negative, if this is at D and this is at E, does that stay the same or change?
It looks the same.
Yeah, I would agree. So in here, we kind of predict it to be the same, right? Anything, it might be a little bit steeper, but that's about it. So I would
Probably just go
Yeah, I
down.
think
little bit because I think it's a hairline. It's hard to see with my Promethean pen.
Because like technically the slope would be the tangent of the slope at that line, and this tangent was a little bit not as steep as
What are you saying?
the other one.
So we already did F. This was F. And then G, we kind of just know is somewhere.
So now this looks like a quadratic. And then this, and then eventually the derivative of this would be a line.
Wait, you can have a derivative be a graph?
Most of the time your derivative will be a graph.
What would
It
that?
has its own function.
Go back to what we wrote. We said from A to C, F is increasing, so F prime is positive. From A to C, is my derivative graph positive?
No.
From C to F, we said the derivative is negative. Is this new graph negative? From F to G, we said it would be positive.
Oh, and
Here's our zeros. We talked about on the original, let's talk about concavity now, because we never really got to look at that. On the original, this is concave down to about here, hence the POI. So we say it changes concavity about there, and it goes to concave up. If it's concave down, the new graph is supposed to be decreasing. Is this decreasing to about that star? And it goes to increasing. That makes this value right here an extrema on the new one, which meant that this was a POI. A POI is a change from concave down to concave up.
What do we do if we have vortex and stuff like that? Isn't it technically-
You have multiple.
ooh, my brain's dead.
That's fine. Just going to talk about one-sided derivatives because that gets to the absolute value stuff we talked about earlier. And then summarize it. A function y is a differentiable on a closed interval a to b if it has a derivative at all interior points. The right-hand derivative must equal the left-hand derivative, meaning as you approach from the left must equal what you approach from the right, meaning
We have to write out the whole thing. Can we just say the left hand equal right hand?
yeah, you know what it means.
1, 0.
You know what it means. So I found out an interesting fact. People building underneath me have never installed what they were installing. And that's why they quit installing, because they were reading the manual and apparently did something wrong.
But you said below us. So do
Those
we
guys that were working below us
so
were
do
trying
we
to fix
have
the
a
heat.
heater?
Oh, that's fine, actually.
So we're gonna have to be in like Arctic.
On Amazon Prime, I ordered a heater for my room. Like a little mini oscillator. Because I was like, I don't want to be cold. I'm cold.
When is
Yeah.
it?
So I ordered, it's getting delivered to school
Are
tomorrow.
they gonna finish it, or they just like?
I was gonna say good luck for the winter.
Yeah.
Yeah, I'm
gonna be bringing in
so SpongeBob entitled.
snow
James
clothes.
Rock, I promise it's
Wow.
wrong. Okay, well, anyway, she says, see this is science, and it's a limit function. I'm not sure what it is, but sometimes we try to pull it up and see if we can solve that. I promise it's related.
I'll go before. All right. First, in order to have a derivative, it must be continuous. That's what we're going to talk about tomorrow with differentiability. So let's apply our continuity rules to see if this works. Is this function continuous?
Yes.
What is f of 0?
0.
The left-hand limit would be?
0.
The right-hand limit would be?
0.
Okay. So f of 0 exists, left-hand limit equals right-hand limit, and the limit equals the domain value.
That's on the corner.
So it is continuous. It is. That's
Is
what we're
it?
going to get to. So now what we want to do is look at the left-hand derivative. So anytime we have a piecewise, we have to look at the left-hand derivative and the right-hand derivative. So left-hand derivative would be of x squared. So that's x plus h squared minus x squared all over h. How it works.
At the top, at the bottom one's the derivative of the top one.
Okay? And then you have 2x plus h minus 2x. Are you looking at my board sheet? Or Michael?
I'm just wondering how you got the 2x plus equals 0. My bad. Okay. H.
Go get it, mine. Okay. So, does the left-hand derivative equal the right-hand derivative? No. So, and you could even check it, because sometimes these might not be the same function, but at the point we're concerned with, the value might be the same.
So it's not differentiable, but it is a continuous function.
Exactly. So this function is continuous, but not differentiable. And we're going to end it at that, because that's totally going to help us for tomorrow and see what we need to see. For tonight, you do have some problems in the book, and they're going to be on graphing. Don't worry about any of this. Okay. So let's modify all of this, because I don't want you doing all of this, and I don't want you doing all this. We're going to do 1 to 21 odds. So that's 11-ish problems. I think these, they have to be grouped together. Like, I think they're matching.
Oh, day 2.
This is day 2.
It is?
Yeah, the day 1 was the worksheet. What?
So day 3?
No. We did the worksheet instead.
This we're doing tomorrow.
I'll look at these, like, I want to give you your test so you can CC them. I'll look at those. If I think it's too much, then I'll send you a reminder and cancel one of the bottom two.
I don't want to see my
We didn't finish the back, so
We're not going to worry about that for now. That was back when I had business calc in here too. And the kiddos in business calc had to understand economics of calculus. And last year I had Andrew who was going into business calc in college, and he wanted to know